All right. So we're going to continue in our discussion on the quadratic formula. So if you remember last class period, we talked about the quadratic formula. And today, what I'd like to do is talk about a particular part of the quadratic formula. So if you remember our quadratic formula, here's our quadratic. Um, ax squared plus bx plus c. Okay. And our quadratic formula, if you remember from last week, when we solve for x, whoops, when we solve for x is the opposite of b plus or minus the square root of b squared minus 4 times a times c, all over 2a. So that is what we call the quadratic formula, and it works on every quadratic. Even if you don't have a B term or a C term, those just go to 0. But we do need to talk about special cases and how they emerge. So there's one part of the quadratic formula that is underneath the square root. That is specifically called the discriminant. The discriminant. Okay. Let me pull up some examples here. All right. So there's different ways in which this number here can emerge. Okay. As we saw in our time period last time, this could be a perfect square. Given the numbers up here, we could look at the discriminant, and it could be that this right here executes to, let's say, 64, to where when you take the square root of 64, you're left with 8, right? Plus or minus from there, plus or minus 8. Okay, this would be a perfect square. And typically, if your discriminant is a perfect square like that, you're probably better off trying to factor this in the original way, either through the AC method or by, if A is 1, looking at two things that multiply to give me C and one thing, and those two same things to add to give me B. But real quickly, if I know my A, my B, and my C, they're all part of what we call the discriminant, we can calculate the discriminant fairly quickly by immediately squaring it and subtracting 4 times AC. So there are some conditions that I want to kind of review with you when it comes to the discriminant. Let me get those pulled up here in my notes. Where did I put that? All right. All right. So if the discriminant, okay, if the discriminant is positive, okay, what that tells us is there are two real solutions, okay, two real solutions. Now, you can also have a 0, okay? The discriminant could be 0. Now, how could the discriminant be 0? Well, it could be because, let's say your C is 0, making this thing 0, and your B is 0, making this thing 0. And at that case, if you have an A times x squared is equal to 0, well, if you divide both sides by A, 0 divided by A is just 0. X squared is 0, meaning x has to be 0. So if your discriminant is 0, that means your x is equal to 0. Okay? But there's one more solution. And before I talk about that, let's review from what we did the first week, where we talked about natural numbers. We started with 1 and we incremented by 1. Whole numbers started with 0 and did the same thing. Integers that go from negative infinity. Shouldn't have started at -5. That would have been easier. All the way to positive infinity, right? It contains all of the whole numbers and the opposite of all the natural numbers. Rational, actually R was for real, so rational was Q, right? Ratio of two integers. And then irrational, not a ratio of two integers. And these were the ones that you knew. And then all of them were under the umbrella of real. Okay. If I look at this in terms of concentric circles, we have the natural numbers, and then we have 0, and that would indicate all the whole numbers. So the whole numbers have 0 and all the natural numbers. Integers, the negatives, and all the natural and whole. Rational, and then irrational over here that's not contained within any of these, but they all exist within the real. Now, there is another set of numbers called the imaginary numbers. And the imaginary numbers are the numbers that if you square root a negative, we'll start with -1. If you square root a -1, that is equal to I. If you square I, that is equal to -1. Okay, so I review all that and introduce these imaginary numbers that are outside of the real numbers. Therefore, the imaginary numbers are not natural, whole, or integer. Integer, I think it was a Z. I apologize. Just now remembered. Um, Integer, rational, irrational, or real. It's not any of this. It's imaginary. So when you have a discriminant, that is less than 0, in other words, negative, you have two imaginary solutions. Okay? Two imaginary solutions. So let me give you an example of what I'm talking about so that we can kind of look at it. All right, we'll look at the problem 2x squared minus 4x plus 13 is equal to 10. Okay. All right, so first things first, I'm going to subtract 10 from both sides because it needs to equal 0 to use my quadratic equation. I'm going to choose to do that. 13 minus 10, that's just 3. And then 10 minus 10 is 0. There we go. So my A is equal to 2. My B is equal to -4. And my C is equal to 3. So remember, my quadratic equation is the opposite of B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. Now I'm going to specifically look at this in here called the discriminant. And the discriminant is the B squared minus 4 times A times C. Okay. Is this greater than 0? Is it 0 or is it less than 0? That's all I'm trying to find out right now. So let's look at my B squared. That's -4 quantity squared minus 4 times A is 2 and C is 3. All right, -4 squared is 16. Minus 4 times 2 is 8. 8 times 3, I believe, is 24. Yep. And I can already tell you that that's going to be negative. So 16 minus 24, that is 16 minus 20 would be -6. So -10. Is that right? I feel like that's not right. 24, 16. Not right at all. It's a -8. -8. So 16, 17, 18, 19, 20, 1, 2, 3, 4. Good. Okay. So this -8 means I have two imaginary solutions. So what does that mean? Well, I've already calculated my discriminant here, so I know what goes underneath the radical. So let me fill in everything else. Opposite of B, B is -4, so opposite of that would be 4, plus or minus the square root of -8. Okay? Divided by 2 times A, and A is 2, so 2 times 2 would be 4. Okay. So now I'll have 4 over 4, which is just 1, plus or minus square root of -8 over 4. Okay. So let me rewrite that portion here. So remember, we had 4 plus or minus the square root of -8 over 4. And what I'm doing is I'm splitting this 4 over the two terms, or under the two terms, I should say. So 4 over 4 plus or minus the square root of -8 over 4. These are common denominators, therefore they carry the same denominator, and then we just add or subtract the top. Okay, so I'm just doing that in reverse. So there's two answers here. The first is 4 over 4 plus square root of -8 over 4, and 4 over 4 minus the square root of -8 over 4. 4 over 4 is just 1. So what I want to do now is I'm just going to rewrite this. So 1 plus square root of -8 over 4. And then here, 1 minus square root of -8 over 4. Okay. So here, notice how I have a negative sign underneath the radical. So if we look at one of the properties of if I have two numbers underneath the radical multiplied together, that's the same thing as the radical of each multiplied together. So here, that's what I'm going to do. I'm going to keep the one where it is, plus, and then I've got, instead of -8, I'm going to do -1 times +8. And it'll be the same here. 1 minus square root of -1 times +8 over 4. All right. So now I can kind of split that up. So I can have 1 plus, and I can do the square root of -1 times the square root of +8 all over 4. So let me just focus on this one. The square root of -1, that's the new number you just learned. And what is the square root of -1? That is the number I. Okay? So this changes then to 1 plus I times the square root of 8 over 4. Now, I can simplify this right here. That 8, it's the same thing as 4 and 2, and this is a perfect square because that's 2 and 2. So I can change this to 1 plus I times the square root of 4 times the square root of 2. The square root of 4 is 2, and the square root of 2, all over 4. That 2 and that 4 are going to simplify. The 2 can go away, and this becomes 2. So then we're left with 1 plus I times the square root of 2 over 2. Now, since I'm dealing with the same numbers here in this -1, that's going to give me the same thing except with a minus. 1 minus I square root of 2 over 2. So the way that this would come across on your answer sheet would be x is equal to 1 plus I root 2 over 2, comma, 1 minus I root 2 over 2. Now, this is an imaginary numbers. This is what's called your real part, and this is what's called your imaginary part. Okay, I have two imaginary numbers. That's why it says two imaginary solutions, because the discriminant was less than 0. Okay. Let's do another example like this, because that can be kind of a confusing concept for many people. So let me pull up my example here. All right, let's do -5 x squared plus 6x plus 15. I'm going to say that's equal to 7. All right, so first things first, I'm going to subtract 7 from both sides. And I have -5 x squared plus 6x. 15 minus 7 is going to be 8. And then 7 minus 7 is going to be 0. All right, so here I've got my quadratic, right, in my quadratic form. So I can easily identify my A, B, and C. A is -5, B is +6, and C is +8. All right, so I'm going to go ahead and go straight into the quadratic equation. We can look at the discriminant immediately if you want to, but we're going to do the opposite of B, plus or minus the square root, and underneath the square root is B squared minus 4 times A times C. And those two terms here are all going to go over 2 times A. All right, well, let's go ahead and kind of plug everything in. So what I'm going to do is just kind of put the skeleton up here. And then everything else is being substituted. So the opposite of b is -6. B squared would be 6 squared. 4 times a, -5, times c, which is 8. Kind of scrunched together there at the end, but you understand what that is. And 2 times -5. All right. So now let's look at the discriminant. 6 squared is 36 minus 4 times -5. That's -20 times 8 all over 2 times -5, -10. All right, so here I want to do the -20 times 8, which is just going to be -160. So let's put that equal to -6 plus or minus the square root of 36 minus, and here we have -20 times 8, and that's going to give me -160. All over -10. All right, so we have -6 plus or minus. Now, 36 minus a minus, that's going to be a positive. And I thought I used an example of where I was going to have two. Oh, no, I used an example where I'd have two real. That's fine. We can do that. Use the wrong example. That's okay. We'll keep going. So 160 plus 36. We can work that off to the side if we need to. That's square root of 196, all divided by -10. All right. So let's see if 196 has a perfect square. How do we do that? Well, one way we could do it is we could do a factor tree and divide it by 2. So if I did 196 divided by 2, I know 9 times 2, this is 18. This is 8. So I divide 2 and 98. And 98 divided by 2. That is 4 times 2 is 8. 118. 9 times 2 is 18. So 49. Okay. So 2 and 49. And then this, of course, is 7 times 7. So we do have a perfect square. We have 14 times 14 is equal to 196. So the square root of 196 is 14. So -6 plus or minus 14 divided by -10. And this will have two answers. First one will be -6 plus 14 over 10. And -6 plus 14 is 8. And then 8 over 10. And we could simplify that. If we divide by 2, that's 4 over 5. All right, then our second option is -6 minus 14 over 10. -6 minus 14 is -20. And -20 over, oh, I'm sorry, this is -10. I forgot to carry that over. -10 there, -10 there, -5 there. So -10 there, -10 there, -20 over -10 is +2. So the answer here for x would be -4 over 5, comma, +2 for our x. just double check that. Well, it gave me the discriminant, and I was right about that. Okay. Very good. Now, let's work one again with two imaginary solutions. All right, so we're going to start with negative 5x squared minus x minus 11 is equal to negative 9. All right. So first things first, add 9 to both sides. Nine plus negative 11 is negative 2. Negative 5x squared minus x minus 2. All right. So our A, B, and C are negative 5, negative 1, and negative 2. All negatives. All right. So if we want to solve for x using the quadratic formula, we're going to do the opposite of B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. All right, so I'm just going to, rather than filling in, I'm just going to switch colors altogether. So the opposite of B is positive 1 plus or minus the square root of B squared. So that's negative 1 squared minus 4 times A, that's negative 5, times C, it's negative 2. All divided by 2 times A, which is negative 5. All right. So we have 1 plus or minus the square root of 1, negative 1 squared is just 1, minus 4 times negative 5, that's negative 20, and negative 20 times negative 2 is positive 40. Divided by 2 times negative 5 is negative 10. Okay. 1 minus 40 is going to be negative 39. So we have 1 plus or minus the square root of negative 39 all over negative 10. Now, let's look underneath negative 39. Obviously, we have a negative 1 times a positive 39, but let's break down 39. Is this a perfect square? I already know it's not because it's an odd number. No two numbers multiplied together will give us an odd out. Actually, that's not true. What am I talking about? 5 times 5 is 25. Hello. But let's see if we can find a perfect square in here. So I know that 3 times 13 gives us 39. But both of those are prime numbers. So it's not going to get any, we can't go any further than that. So if I do the negative of 39, remember from my radical roots, what I can do is the square root of negative 1 times the square root of 39. Because negative 1 times 39 gives me negative 39. Square root of negative 1 is I. So I have 1 plus or minus I times the square root of 39 all over negative 10. So this gives me two answers. 1 plus I square root of 39 over negative 10, and 1 minus I square root of 39 over negative 10. All right. So we can see that factoring is a huge part of algebra, and that we can get into situations where we have to go beyond the real numbers and begin to incorporate this thing called imaginary numbers in order to solve our problem. Okay. Let me work one more of this type, and that'll probably be enough for today. So let me do two new colors here. Of negative 5x squared minus 3x minus 7 is equal to negative 3. First things first, I'm going to add 3 to both sides. That effectively is going to give me negative 5x squared minus 3x minus 4 is equal to 0. All right, so another situation in which all 3 are negative. A is negative 5. The coefficient B is negative 3, and the coefficient C is negative 4. So if we solve for x, x is the opposite of b, plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Opposite of b, positive 3. B squared, negative 3, quantity squared, minus 4 times AC, negative 5 times negative 4, all over 2 times negative 5. Wait, 3 plus or minus square root of negative 3 squared is positive 9, minus 4 times negative 5 is negative 20. Negative 20 times negative 4 is positive 100. No, negative 20 times 4 is positive 80. All over 2 times negative 5 is negative 10. All right, so that is 3 plus minus square root. 9 minus 80 would be negative 79. I'm sorry, negative 81. That's what it is, negative 81. I went the wrong way on that. Negative 81 divided by negative 10. Now, this one actually has the benefit of 81 being a perfect square. But let me go ahead and break this down. I kind of skipped this step last time, so I'll incorporate it here. Negative 81, I'm going to write as negative 1 times positive 81. Okay, so now I have 3 plus or minus the square root of negative 1 times the square root of 81, all divided by negative 10. We have 3 plus or minus the square root of negative 1. Whoops, got off screen there. The square root of negative 1 is I. and the square root of 81 is positive 9, all over negative 10. All right, so we have two answers, 3 plus I9 over negative 10, and 3 minus I9 over negative 10. Now, I can't combine my real and my imaginary part. So if this has an I, it can't combine with something without an I. That's why we keep it separate like that. But this will be effectively my x's. All right, that is all for today.